everyone. So in this section, we will look at some steps for solving hydrostatic problems and then go through a few examples showing how to solve. Okay, so let's look at some steps. The first thing I suggest, step one, is to draw a picture. So in your picture, you should show any boundaries between types of fluids, any surfaces, pistons, or surfaces that are open to the air. So we want to show that as well as the shape of the container. Then when you have that, the next thing that we can do is find P naught. Determine the pressure at the top of the region of fluid that we're interested in. Generally, there's three different cases here. One is that it's open to the atmosphere. And in that case, if it's open to the atmosphere, then we know that P naught is atmospheric pressure. Another case could be that there's a surface on top or a weight, something that's exerting a force on the top of the fluid. In that case, we'll use the definition of pressure, force per unit area, in order to calculate the pressure at the top of the region. The third case is that maybe we have a different type of fluid on top of another fluid. Then we'll have to find the pressure at the bottom of that fluid, which becomes the top of the next fluid region. And I'll show an example with that, but in that case, our P naught is the pressure of the fluid at that point. Okay, once you have P naught, then there's two different things. We may have to apply the horizontal line rule if necessary, or find gauge pressure if we're asked for that in the question. And then lastly, we're going to apply the hydrostatic equation and solve for the pressure at the desired depth. Okay, let's look at the first example. Determine the depth to which you would have to dive to experience water pressure that is twice atmospheric pressure. And then estimate the net air pressure force exerted on your eardrum of area 0.5 centimeters squared if you suddenly dove to this depth. Okay, so it looks something like this. This is the top of the water, and then we're going to dive under to a point where the pressure is 2 times atmospheric pressure. We know at the top of the water that it's open to the environment, so that has to be atmospheric pressure there. All right, so also just to remind you, two helpful constants are atmospheric pressure, 1.013 times 10 to the 5 pascals, and then the density of water, which is 1,000 kilograms per meter cubed. Okay, so we've drawn our diagram and determined the pressure at the top, so now we can apply the hydrostatic equation, P equals P naught plus rho GH. So in this case, we have 2 times atmospheric pressure equals 1 times atmospheric pressure plus rho GH. So rearranging this, 1 will subtract here, we'll get PA equals rho GH, which then gives me H equals atmospheric pressure over the fluid density times G. And we can plug in the numbers at that point. So this is 1.013 times 10 to the 5 pascals divided by 1,000 kilograms per meter cubed times 9.8. And it turns out that this is a depth of 10.3 meters. And that's a significant pressure change that we'd be able to feel going 10.3 meters under the water. All right, so in the next part, we're asked which force this corresponds to that it would be exerted on the eardrum at this depth. So just a note about this. When you feel a pressure change in your ears, that's because there is a net pressure difference between the inner ear canal and outside the ears. So if it looks something like this, and this is your eardrum, normally we have atmospheric pressure inside. So that would exert a force of atmospheric pressure times the area. And if you go in an airplane or underwater and there's no way to release, so in an airplane you can kind of yawn or pop your ears to release that pressure and allow for it to equilibrize. Otherwise, we're going to have a pressure difference from inside to outside the ear. So at this depth, we're going to have 2 times atmospheric pressure times the area pushing onto that eardrum, which creates a net force. Okay, so the net force in that direction will be 2 PA minus 1 PA, which is atmospheric pressure times the area. And we have an area of 0.5 centimeters squared, which is 0.5 times 10 to the negative 4 meters squared. Okay, so I get 1.013 times 10 to the 5 pascals times 0.5 times 10 to the negative 4 meters squared, giving me a net force of 5.07 newtons. All right, let's look at example 2. All right, in a huge oil tanker, salt water has flooded an oil tank to the depth of H2 equals 5 meters. On top of the water is a layer of oil, H1 equals 8 meters deep. The oil has a density of 700 kilograms per meter cubed, and the water has a density of 1,025 kilograms per meter cubed. Find the pressure at the base of the tank. A diagram is really helpful here so that we can see the setup. So we've got this tank open to the air on the top here, and then there's oil with its density and salt water, and I've written in the heights of each part here. And so this is an example where we do have more than one type of fluid on top of each other. So let's look at how to solve. Okay, we want eventually the pressure here at the bottom, P2. If we look at the pressure at the top of that region, this is the pressure at the bottom of the oil. So we're going to have to apply the hydrostatic equation twice, once to find the pressure at the oil-water surface right here, and then once again to find the pressure at the bottom of the salt water. All right, so just looking at this region here, we have P0 equal to PA at the top of the air, and then we can plug it in here using the density of oil and this height of 8 meters. So I've plugged that in to find the pressure at this surface here, P1. So P1 is 1.56 times 10 to the 5 pascals. All right, now that we have the pressure at the top of this region, this becomes P0 when we apply the hydrostatic equation again, now to find P2. So P2 will be 1.56 times 10 to the 5 pascals, plus the density of salt water, 1,025 kilograms per meter cubed, G, and then this height of 5 meters. And that gives us our final pressure here of 2.06 times 10 to the 5 pascals at the bottom of the tank. Determine the minimum gauge pressure needed in the water pipe leading into a building if water is to come out of a faucet on the 12th floor of a building, 38 meters above the base of the pipe. All right, so it looks something like this. This is the pipe. We want to find the gauge pressure here that allows the water to flow out at the top of the building, 38 meters above that point. In order for the water to flow out of that pipe, its pressure has to be at least equal to atmospheric pressure. Likely it's greater, but at the minimum it has to be equal to atmospheric pressure. So we do have P0 at the top equals PA in this case. So now with our diagram, let's apply the hydrostatic equation. And this time we're solving for gauge pressure. So we know P0 equals PA, and the gauge pressure is the difference between the absolute pressure at that point and the atmospheric pressure. And if we subtract them, we can see in this equation, by rearranging, that equals rho GH. So it's a simple calculation here. We can just plug that in. 1,000 kilograms per meter cubed for the density of water times 9.8 meters per second squared, 38 meters, gives me 3.72 times 10 to the 5 pascals for the gauge pressure needed at the bottom of that pipe. All right, next example. A bent tube is closed at one end as shown. What is the absolute pressure at the top of the closed tube? All right, so it looks like this on the diagram. We have this closed end, and then it opens up here, and we have a depth of 100 centimeters of water on the left side. So we don't have a clear way to determine the pressure at this closed end on its own. So instead we want to make use of the horizontal line rule in this case. So the horizontal line rule, to review, says that the pressure in a connected fluid of one type anywhere along that horizontal line will be equal. Any horizontal line anywhere in the fluid. So we can draw a horizontal line from this closed end over to this side, and we know that the pressure here, P1, must equal this pressure P2 at that closed end. So we can then apply the hydrostatic equation, P2 equals P1, which is P naught plus rho F GH. And this is easier to calculate over here because we know that the pressure at this top of the region is equal to atmospheric pressure on this side. So we have atmospheric pressure, 1.013 times 10 to the 5 pascals, plus the density of water times G times just this height here. My diagram's not quite to scale, but that should be 0.6 meters. We have 100 centimeters minus 40. And calculating that, we get 1.072 times 10 to the 5 pascals. All right, one more example in this section. Okay, a bent tube is partially filled with water, density 1,000 kilograms per meter cubed, and partially filled with oil, density 900 kilograms per meter cubed, as shown. Calculate the gauge pressure at the closed end of the bent tube. All right, so I've drawn this out and I have the solution here, which I'll explain. So the tube looks like this. You can look at the diagram in the lecture slides. So we have oil at the top here, and then all of this is water in this region. All of that's water, all the way up to the closed end here where it's labeled P3 for the pressure. Ultimately, we want to find the gauge pressure here, P3, but again, there's no one step to do that at the closed end of a tube, especially when we have other fluids in the other parts of the container. Okay, so then we have oil here at a depth of H. We can draw a horizontal line here to connect P2 to the bottom of the oil. We don't want to do that here because this is going water to oil, but if we do it right along this line at the bottom of that oil, we're still within the water region. All right, so we know because of that horizontal line that we have P1 equals P2. Now, P1 at the bottom of the oil, it's easy to write out, that's all oil, and at the top of the region here, this is atmospheric pressure. It's open to the environment at the top of the oil. So we get P1 equals PA plus rho oil GH here. And then if I try to find this side from the horizontal line rule, P2 equals P3 at the top of the region plus rho water, it's water here, G and then D. Now in this step I can equate them. So I'm applying the rule here, putting P1, this expression, is equal to P2, this side here. And I know I want to find gauge pressure. So what I want to solve for at this point is P3 minus PA. Since the gauge pressure is equal to the absolute pressure P3, the closed end in this case, minus atmospheric. So I'm getting that onto one side. I'm doing P3 minus PA, which leaves me with rho oil GH minus rho water GD. You can stop and do that algebra if you like. Okay, so then this itself is the gauge pressure, and then we can plug in numbers at that point. So we have 900 density of oil, 9.8 meters per second squared times 0.75, this height here, and then 1,000 kilograms per meter cubed, 9.8 meters per second squared, times 0.25 meters. And if you calculate this, I've circled the answer here, you should get 4,165 pascals for that gauge pressure at the closed end. All right, let me know if you have any questions, and I will go on to Pascal's principle next.